Okay, hello everybody. Been a while again. I haven't quit on this book just yet. Just been busy again with stuff, and also something happened to my desktop. I'm not sure what happened, but get a black screen whenever I turn it on. Like black screen literally, in that there's no display output. I might be suspecting that it might be the GPU. It is an old one. It's like a 2070, and it has been through a lot in the past. So that probably would have, you know, I think it gave out. But I run Arch, and every time you update, you don't know what you're gonna get. So today I'm actually gonna be using my laptop, just connected through this weird setup right now. And again, I've redone my streaming setup again, or at least the OBS configuration. So hopefully I get sound and everything is going to be good. So yeah, let's start. So this next chapter here is chapter 17. We're going through devices and modules. And my hope is that this one's going to be more action-packed than the other chapters that we've previously read. At least that will, I'm hoping that we'll get to some coding eventually. So, yeah. Okay, let's do it. So in this chapter, we discussed 4 kernel components related to device drivers and device management. Hold on. Already we're off to not a good start. Why is this? Let's see. Oh, weird. Let's see here. My pen is different on Windows. But okay, whatever. I'm so used to highlighting, so maybe I could highlight like this. This. Let's do this. Nah. Okay, whatever. But I didn't know I can annotate. All right, let's just do it. Okay, so in this chapter, we discussed 4 kernel components related to device drivers and device management. Device types. Okay, classifications used in all Unix systems to unify behavior of common devices. Modules. The mechanism by which the Linux kernel can load and unload object code on demand. Kernel objects. Support for adding simple object-oriented behavior and a parent-child relationship to kernel data structures. And in sysfs, a file system representation of the system's device tree. Okay, so device drivers come in like 4 different forms and concepts. So yeah, so device types. In Linux, as with all Unix systems, devices are classified into one of 3 types. You have block devices, which has that random I/O behavior. You have character devices, where you stream pretty much data 1 byte at a time. And you have network devices, which passes packets back and forth. So these are often abbreviated as BLK devices or BLK devs, which is block devices, and are addressable in device-specified chunks called blocks, and generally support seeking. So seeking means that randomness to go from one part of the device to another just to read data. And then, so the random access of data. So example block devices include hard drives, Blu-ray discs, and memory devices such as flash. And I guess that's considered to be SSD now. So block devices are accessed via a special file called a block device node and generally mounted as a file system. We discussed file systems in chapter 13, the virtual file system, and block devices in chapter 14, the block I/O layer. So often abbreviated CDEVs, character devices are generally not addressable, providing access to data only as a stream. So generally of characters, and these characters are bytes. Okay, so they're like 1 byte at a time. It's not necessarily like readable characters. It could just be like garbage, but that can be interpreted as like an 8-bit piece of data. So example character devices include keyboards, mice, printers, and most pseudo devices. Character devices are accessed via a special file called a character device node. Unlike with block devices, applications interact with character devices directly through their device node. Okay? So sometimes called Ethernet devices after most common type of network devices. Network devices provide access to a network, okay, such as the internet, via a physical adapter such as your laptop's 802.11 card, and a specified protocol such as IP. Breaking Unix's everything is a file design principle. Network devices are not accessed via a device node but with a special interface called the Socket API. Linux provides a handful of other device types, but they are specialized to a single task and are not common. One exception is miscellaneous devices, so MISC. Okay. Miscellaneous devices enable a device driver author to represent simple devices easily, trading functionality for common infrastructure. So, not all device drivers represent physical devices. Some devices are virtual, providing access to kernel functionality. Okay? So we call these pseudo devices. Some of the most common are the kernel random number generator, accessible at dev random and dev urandom. Oh, I didn't know this. Okay, so all this time I've always seen the /dev/random and /dev/urandom. Never knew what they were. So these are like virtual devices that provide different types of functionality. It allows you to kind of like in your program as you're coding, access at least these devices as if they were like real like disks, for example, and you can like write to them or read to them. And I think we'll see that down the line. And the null devices, so /dev/null, where you can actually just pipe all your output or redirect all your output specifically to this this dev null device, which acts as like nowhere land. And zero device accessible at dev zero, and a full device accessible at dev full, and a memory device accessible at /dev mem. So most device drivers, however, represent physical hardware. Okay, so again, everything in like Linux world is kind of mounted in a file system way. So like devices can be accessible and interfaced through file system paths. So that's the reason why we have this /dev/whatever here. So modules, despite being monolithic in the sense that the whole kernel runs in a single Azure space, the Linux kernel is modular, supporting dynamic insertion and removal of code from itself at runtime. Related subroutines, data and entry and exit points are grouped together in a single binary image, a loadable kernel object called a module. Support for modules allows systems to have only a minimal base kernel image with optional features and drivers supplied via loadable separate objects. Modules also enable the removal and reloading of kernel code, facilitate debugging, and allow for loading of new drivers on demand in response to the hot plugging of new devices. Oh, that's crazy. So it's dynamic. It's like a DLL, or like dynamic library that gets inserted in and out of basically runtime memory. So the chapter looks at the magic behind modules in the kernel and how you can write your own module. So hello world. So unlike development on core subsystems of the kernel, which is much of the material discussed thus far, module development is more like writing a new application, at least in the sense that modules have entry points and exit points and live in their own files. It might be cliche, but it would be a travesty to have the opportunity to write hello world and not capitalize on the occasion. So here is a hello world kernel module. So it's basically a C file, except that you include all these Linux headers. And then we'll have a static int hello init. Okay, so this is the init function called when the module is loaded. So we run this whenever we load the module. So it's just an alert. And then I bear a charmed life. And then exit. So I guess all modules have an initialization and an exit. So exit is called whenever the module is removed. So hello exit here. And then we actually, I guess, register them here with this module init and module exit. So the pointers, the function pointers, right? So for module init, we pass in the function pointer to hello init. Okay. And then for exit, we pass in the function pointer hello exit. And I think this is by good practice. We had to include these module license, module author, and module description pieces. This is a simple kernel module as one can get. The hello init function is registered as this module's entry point via a module init. The kernel invokes hello init when the module is loaded. The call to module init is not actually a function call, but a macro. Oh, okay. So these are not function calls, they're macros that assigns its sole parameter as an initialization function for this module. All init functions must have the form int my init void. So like this, static int and then my init void. It takes in no arguments. Okay, because init functions are typically not directly invoked by external code, you don't need to export the function beyond file level scope, and it can be marked as static. So statics are kind of like private functions in C in this case. So init functions return an int. If initialization or whatever your init function does was successful, the function must return 0. On failure, the function must unwind any initialization and return non-zero. So unwind meaning undo any like state changes that happened to the kernel, I guess. So this init function merely prints a simple message and returns 0. In actual modules, init functions register resources, initialize hardware, allocate data structures, and so on. If this file were compiled statically into the kernel image, okay, so meaning not dynamically loaded, not like a module, just statically in code inside that binary, inside that kernel binary, the init function will be stored in the kernel image and run on kernel boot. The module exit function registers a module's exit point. In this example, we register the function hello exit. The kernel invokes the exit point when the module is removed from memory. Exit functions might free resources, shut down and reset hardware, and perform other cleanup before returning. Simply put, exit functions are responsible for undoing whatever the init function and lifetime of the module did, essentially cleaning up after the module. After the exit function returns, the module is unloaded. Exit functions must have the form void main exit and then void no arguments. As with the init function, you probably want to mark it as static. If this file were compiled into the static kernel image, the exit function would not be included and it would never be invoked, because if it were not a module, the code could never be removed from memory. Okay. So here's an important thing that I'm starting to get. Like, kernel modules are supposed to be written in a way where they can actually be statically compiled into the kernel and not just running as modules. So we can run a kernel module or we can build a kernel module in like two ways. One, like statically with the kernel as if it was like real burnt into kernel code, or we can build it in a way where it gets added into runtime later. And when it gets added into runtime later, you have that init and exit process. But if it's statically compiled into the kernel, you'll just have like an init process for it, but you won't have like an exit, because that doesn't really make sense. Okay, so the module license macro specifies the copyright license for this file. Loading a non-GPL module into memory results in the tainted flag being set in the kernel. The copyright license serves two purposes. First, it is for informational purposes. Many kernel developers give bug reports less credence when the tainted flag is set in when the tainted flag is set in an oops, because they presume a binary only module. Okay, that is a module that they cannot debug was loaded into the kernel. Second, non-GPL modules cannot invoke GPL only symbols. Okay, there's a lot of rules here. We cover GPL only symbols in the section export symbols later in this chapter. Finally, the module author and module description macros provide respectively the module's author and brief description of the module. The value of these macros is entirely informational. So building modules. Okay, so this is what we need so that we can start writing our own. So in the 2.6 kernel, building modules is easier than in previous versions thanks to the new kbuild build system. The first decision in building modules is deciding where the module source is to live. You can add the module source in the kernel or to the kernel source proper, either as a patch or by eventually merging your code into the official tree. Alternatively, you can maintain and build your module source outside the source tree. Let's probably try to just do it inside the source tree. Living in the source tree, yes. So ideally, your module is an official part of Linux and thus lives in the kernel source tree. Getting your work into the kernel proper might require more work at first, but it is the preferred path because when your code is in the Linux kernel, the entire kernel community can help maintain and debug it. When you decide to place your module in the kernel source tree, the next step is deciding where in the tree your module is to live. Drivers are stored in subdirectories of the drivers / directory in the root of the kernel source tree. Inside drivers / class, type, and specific device further organizes drivers. For example, drivers for character devices live in drivers char, block devices live in drivers block, and USB devices live in drivers USB. The rules are flexible because many devices belong in multiple categories. For instance, many USB devices are character devices, but they reside in drivers USB, not drivers char. Despite such complications, when you get the hang of it, the organization is understandable and descriptive. Yeah, so they're saying how like character drivers, like there is a possibility because there's like USB keyboards, and I think keyboards are considered to be character devices here. Okay, so let's assume you have a character device and want to store it in drivers char. Inside this directory are numerous C source files and a handful of other directories. Okay. Drivers with only one or two source files might simply stick to their source in... Oh, I just did it. What did I do? Sorry. I just did it. What did I do? How did I get the highlight? Oh, it's only double clicking. Okay, so whatever. Drivers with only one or two source files might simply stick to their source in this directory. Drivers with multiple source files or other accompanying data might create a new subdirectory. There is no hard and fast rule. Presume that you want to create your own subdirectory. Let's further assume that your driver is for a fishing pole with a computer interface, the Fishmaster XL3000. So you need to create a fishing subdirectory inside drivers char. Next, you need to add a line to the makefile in drivers char. So you edit drivers char makefile and add this fishing. Okay. Ooh, so this is a good example. I think this is one that we can do. Okay, we can follow this one. Okay, so this causes the build system to descend into the fishing subdirectory whenever it compiles modules. More likely, your driver's compilation is contingent on a specific configuration option. For example, perhaps config fishing pole. Okay, so we can add that. So see the section managing configuration options later in this chapter for how to add a new configuration option. I think we could just build with it for now. In that case, you would instead add the line. Okay, so in case if this based off of this configuration, right? Add the fishing. This one is just adding it straight up. Okay. So finally, inside drivers char fishing, you add a new makefile with the following line: object m plus equals fishing.o. So okay. So char makefile, you add the directory, and then inside our driver directory, we'll add in the object file. Okay. So the build system now descends into phishing and builds the module phishing.ko and from phishing.c. Yes, confusingly, you write an extension of .o, but the module is compiled as ko. So as before, more likely your phishing poll's driver compilation is conditional on a configuration option. So you probably want to write the following: obj config phishing poll plus equals phishing o. And that's inside the driver's char phishing directory. So one day your phishing poll driver might get so complicated, auto detection of phishing line tests is just the latest must-have, that it grows to occupy more than one source file. No problem, anglers. You simply make your makefile read the following. So then we have these object files associated with the phishing objects. Okay? And then what? How does it know? Plus equals phishing.o. Because there's two files here. There's phishing main and phishing line. This is phishing objects. Okay, so now phishing main.c and phishing line.c will be compiled and linked into phishing.ko. Oh, okay. Whenever config phishing poll is set. I don't understand make that well, so I'm guessing it's implied. Finally, you might need to pass to the C compiler additional compile flags during the build process solely for your file. To do so, simply add a line to the following in your makefile: extra C flags plus equals -d titanium poll. Okay, so if you opted to place your source files in the driver's char and not create a subdirectory, you would merely place the preceding lines preceding lines that you place in your makefile into driver's char phishing into driver's char makefile. Sure. So to compile, run the kernel build process as usual. If your module's build was conditioned on a configuration option, as it was with config phishing poll, make sure that the option is enabled before beginning. Okay. So then living externally. If you prefer to maintain and build your module outside the kernel source tree to live the life of an outsider, simply create a makefile in your own source directory with this single line. Okay, object m specified phishing.o. Okay, this compiles phishing.c into phishing.ko. If your source spans multiple files, 2 lines will suffice. Okay, so same thing. This example compiles phishing main.c, okay, phishing line into phishing ko. The main difference is in living externally is the build process, but your module lives outside of the kernel tree, so you need to instruct make how to find the kernel source files and base makefile. And this is also easy, okay? So we add this into our makefile externally, okay? And this is to tell us where the kernel source is at. So in the example, kernel source location is the location of your configured kernel source tree. Recall that you should not store your working copy of the kernel source tree in USR source Linux, but somewhere else, easily accessible in your home directory. So now installing modules. Compiled modules are installed into libmodules version kernel, where each directory under kernel corresponds to the module's location in the kernel source tree. For example, with a kernel version 2634, that's the one that we have, the compile phishing poll module would live in libmodules 2634 kernel drivers char phishing ko if you stuck it directly in the driver's char. The following build command is used to install all compile modules into the correct location. So make modules install, which we have done before, and this needs to be run as root. So sudo make modules install. Okay, so generating module dependencies. The Linux module utilities understand dependencies. This means that module chum, CHUM, can depend on module bait. Oh, I think these are phishing terms. And when you load the chum module, the module loader automatically loads the mate module. Okay, so you can have modules that depend on each other, and you can also specify the order, I guess. So this dependency information must be generated. Most Linux distributions generate mapping automatically and keep it up to date on each boot. To build the module dependency information as root, simply run detmod. To perform a quick update, rebuilding only the information from modules newer than the dependency information, run as root, detmod-a. The module dependency information is stored in the file libmodules version modules.det. Okay. Sure. So loading modules. The simplest way to load a module is via insmod. This utility is basic. So this is like how to load our compiled KO file eventually. It simply asks the kernel to load the module you specify. The insmod program does not perform any dependency resolution or advanced error checking. Usage is trivial. As root, simply run this command, insmod module.ko. Here, module.ko is the file name of the module that you want to load. So I'm guessing it knows to look for the directory because it's in a specific directory that you had specified. So here, module.ko is a file name. Okay, so to load the phishing pole module, you would run this command as root, insmod phishing.ko. In a similar fashion, to remove a module, you use the rmmod utility. So to remove, as root, simply run the following, where module is the name of the already loaded module, rmmod module. So sudo rmmod module. For example, this command removes a phishing pole module, so rmmod phishing. So in this case, we have to run as root, so sudo rmmod phishing. Holy moly, there's a lot of stuff here. Okay, so these utilities, however, are unintelligent. The utility mod probe provides dependency resolution, error checking, and reporting, configurable behavior, and more advanced features. Its use is highly encouraged. To insert a module into the kernel via mod probe, run as root, sudo mod probe, I'm guessing phishing. Here, module is the name of the module to load. Any following arguments are taken as parameters to pass to the module on load. Okay, see the section module parameters for a discussion on module parameters. Okay, so mod probe is like the newer way to do it than insmod, I'm assuming. We'll probably try both just to see. So the mod probe command attempts to load not only the requested module, but also any modules on which it depends. Oh, that sounds useful. Consequently, it is the preferred mechanism for loading kernel modules. Okay, let's just do it mod probe way if we were to make our own modules. The mod probe command can also be used to remove modules from the kernel. To remove a module, run as root, run sudo mod probe -r modules. Okay. Here, modules specifies one or more modules to remove, unlike rmmod. Mod probe also removes any modules on which the given module depends if they are unused. Section 8 of the Linux manual pages provides a reference on its other less used options. Okay. I think this is a good break for coding time. Okay, so let's do this. Have a Windows terminal up, and let me bring that PDF down here so I'm not flipping constantly. That looks okay. Okay, so first things first, what are we supposed to do? Okay, so what we're supposed to do is we're going to create a folder. For example, let's create a phishing directory under drivers char. So I'm just gonna go here and I'm gonna do let's see, Linux. Okay, so I could just do make dir drivers char, and I'm gonna say phishing. Okay. And then if I do this, I should see nothing. Okay, that's great. Okay, so then we have to edit our drivers char makefile to have this line here with the phishing directory specified. So if I were to just look at drivers char make file should be somewhere there. Okay, and we just need to add a new I guess line maybe. So if I go all the way, oops, that's too far. Maybe everything. You know what? Let's just do it up on top. Okay, object M plus equals fishing, like that. Okay. And then, actually, we shouldn't quit yet. Okay, so we're gonna assume we're going to just compile it as is, as a module. And then finally, inside drivers char fishing, we need to add a new makefile with the following line. Okay, object M fishing.o. Okay, so we're going to have to create a new file. So it's going to be e drivers char fishing makefile. Okay. So then now we have object M plus equals, so this one right here, fishing.o. Okay, so that takes care of the makefile. We're not gonna have multiple files or also like have configuration options right now. We're also not gonna have compiler flags. Let's just keep it simple. So then we're gonna have to create our modules. So in the same directory, drivers char fishing makefile. Well, I guess we can just do this. Something like this. Fishing.c. Something's wrong. It's like slow. Okay, there we go. Okay, so okay, we create a new file, fishing.c. Now we're gonna have to do this, right? So include Linux init h, Linux module h, Linux kernel h. So this is gonna be our driver, our kernel module. So include Linux init.h, include Linux module.h, include Linux kernel.h. And then we're gonna say static fishing init. Let's just call it fishing init. Static int, I guess. Static int. Oh, this font size might be too small, huh? Let's do. How's this? Okay, that looks better. Okay, so. Yeah, so we're gonna include these headers. Do static int hello, or not hello, fishing init void, and we're just gonna do print k. Print k. Let's see, current alert. The fishing module has been loaded. Let's just do that. Okay, and we have to return 0 if it's successful, based off of what the book said. And then we'll have I guess an unmount routine, static void fishing exit, void again. Okay, then print k, current alert, and I guess it'll be the fishing module is being unloaded. Okay, and that's actually just like tag our stuff right there. Average dev, back to our roots. Okay, and void, so we don't need to return anything at all. Okay, so that's void. Okay, now next we specify the routine, which one is actually initialization one with the module init. That's going to be fishing init. Okay, and then we'll have a module exit with, oops, it keeps trying to copy it. Wake up. Okay, now Module license, module author, module description. I'm just gonna copy and say it's GPL. Then author is going to be average dev. Okay, and then module description. Phishing module from the book. Okay. Okay, cool. So I'll ignore all these errors, I guess. I think that's it, right? So now we have to build this thing. So same as always, right? We can just build. We should probably build this in our VM, but let's just see all this. Okay, so building. This is living externally. Living externally, that's fine. We have to compile, so we're gonna compile with make j whatever, and then after that we're gonna do sudo make modules install, and then I guess sudo make install. So let's go back to our VM and do that. Okay, so we were to go to the console, kind of just shrink this down. Okay. All right. So, yeah. So let's go to, this is where we're at. So, average dev, CD Linux. Okay. So again, let's make sure that we have our edits here as appropriate. We've already included the phishing directory in the driver's char make file, so that should be there. Oh, we're still on our timer example. I wonder if we should make a new branch. Should we? Hey, how come we're missing a file? I'm so confused. We should have more file, right? We should have the phishing.c file. We should have the phishing directory in general. Untracked files. Oh, right here. Drivers phishing. Okay. What should we do? Should we create a new branch, or should we just roll with it? Let's roll with it. So make j 16, and then we'll be back. Okay, so now here the kernel compilation process said that it compiled our modules now, and as expected, we have our .ko file here. If it's we can see it better. How do we zoom in? Let's see. View, zoom in. Okay, so right here we have that ko file there. So we can just do something like sudo make modules install. Password. Okay. So now it's installing all the modules. Maybe we can catch it. Probably not. It's okay. So we'll install all that stuff, and then we didn't really need to compile any. We don't need to load a new kernel or anything, right? So we can just reboot maybe, or actually let's try not rebooting. Let's do this. Dmessage grep average dev. Okay, we have all that still. So we can do mod probe, right? I think this is mod probe phishing. Okay, error inserting. Oh yeah, we had to do sudo mod probe phishing. Okay, something happened, so we had to use mod probe to, I guess, install it, and let's dmessage average dev. Probably, what was it? Oh, the phishing module has been loaded. Maybe we should just do grep phishing. Okay, so yeah, right there. So we're able to load the driver now, and then how do we unload? So I think it's mod probe dash R fishing. So let's unload it. Forgot sudo. Okay, so now we demessage fishing again. So, why? Let's take a look. So generating modules, dependencies, loading modules. It's not dash R. How do we unload? Yeah, right here. Oh, I know why. I found the bug again. It's because I had the comma. Arg. Okay, so let's recompile. Okay, so what is it? Make J16, and then I can just probably do something like this. Make modules install. So make J16 and sudo make modules install, and just go right at it. Now see y'all again. Okay, so that seems to work now. I'm also installing video editing software at the same time, but anyway, so we can just do what is it? Clear sudo mod probe fishing. So that should get us to load the module. So we can do demessage grep fishing module. And okay, we have 2 loaded because from the other one. And then now let's also remove the module. And then let's check it out. Okay, so now we have our exit running. So the fishing module is being unloaded. So that's good. Yeah, we wrote a simple driver. Very, very simple kernel module. It wasn't too hard to compile since it was all in the tree, the kernel source tree. And so, yeah, that's as much as I want to get to today. I just want to be able to compile, do a little bit of programming. I think we're going to continue the rest for managing configuration options next time. But yeah, good start. Sorry for the shakiness. New environment, not used to it, especially on a laptop keyboard. So thank you, and hopefully I'll see you soon.